The presentation today is some of our work, but we've been collaborating forever. So we actually started our company when someone suggested I speak to Peter, who I believe you have some of his early microscopes, and said, yes, my microscopes generate a lot of data. Maybe we could have a solution for that. And so that's how we started. And ever since we had a collaboration, we had several students from EPFL doing their masters with us. We hired several people from EPFL. And yes, so there's a big representation. And also there's people from here who are responsible for the work we do. Also, it's not just that, is that there's a lot of knowledge that comes from here. It's compression, JPEG 2000, wavelets, etc. All that know-how really was born here. And so for us to have that easy access when I have a problem, we don't know how to do something, we know, or at least my colleagues, especially the ones that come from EPFL, they know who to ask. Come and say, okay, and I'm amazed. I say, like, okay, you know, you're doing a master's, and like we did a PhD, we're researchers, and how did you solve this in 2 weeks? And we hadn't solved that problem for years. And so, yes, you know, I just went and I talked to my professor, and he said, just do this. And so it helps a lot. So this closeness helps a lot. And as well, when you develop a product, you have to understand what people want, what they need. And that's the main thing. And so the presentation today is this. So everyone says, well, I want to save raw data, but it's too big. What we didn't know is what do people actually mean by raw data. So first we asked, yes, but why do you want to save raw data? And also I just came back from Adam and he said, well, lots of times I just don't want to save raw data because, you know, like it's not needed. So, but we wanted to focus on when you do want that. Why do you want that? Well, first of all is that image processing has been done for now for the human eye. So Photoshop, to process from a raw image to an image that you can see and I can show on the PowerPoint, takes about 1 million operations per pixel. So this was years ago. Like now with AI, maybe it's 1 trillion operations per pixel, I don't know. And as you see, however, it looks way better to us. So that image on the right contains 100 times less information than the one on the left. But to us, it looks better. And so if it's a human problem that we want to solve, you know, if we want to find strawberries because we're hungry, then the processed image through the visual system, that's completely fine. If we want to do something else, maybe it's less good. So indeed, the human visual system is rather complex. It has lots of compression already integrated in it. You have your well, I explain it here, but I know biologists know a lot better how this works than I do, so forgive me if it's not accurate, but you have your retina that already has some pre-processing with the ganglions at the back of your cones and rods, and then that information is reduced by about a factor of 10, and then it goes to your visual cortex at the back of your brain, and then your conscious, only later, actually, and a lot less information, maybe 1 million tons of information is sent to your conscious brain. And one thing that I find fascinating is that you know how we all have this blind spot at the back of the eye. Well, the fovea, which is the area where we have accurate color sensitivity, is just as big as your blind spot. But we have the impression not to see the blind spot at all and to see everything in color. But that is because our brain processes the information so much. So what does a camera do? And so when I talk to someone, I say, what do you mean by raw data? They always say, well, basically they say it's what the previous person gave you. So if I talk to a scientist, they say, what is what I get out of the microscope? If I talk to the person who builds a microscope, they say, well, it's what I get out of the camera. If I talk to the guy who gives me, who makes a camera, they say, well, it's what I get out of the sensor. If I talk to the sensor guy, he says, well, it's whatever I get out from the pixel. And no one knows all of the processing. Of course, there's a lot of value. So that if you buy a Hamamatsu camera, it's very high end, it's very expensive, and there's a lot of value. And a lot of that value is to make sure that the image is processed correctly so that it's what you think is raw data. And the same if you buy a high-end instrument, the same concept. But it's more of a, what is a raw image is more of an ideal. So as an example, like if you don't have a 60, most biological images are 16 bits, you don't have a native 16-bit pixel. So the pixel, they, like when you read it out, you have two readouts of 11 bits, they're merged together. If you take a hammer macro image and do some statistics, you see a little blip where they're merged together, but that is done very carefully, right? So what do you have? So first you have your sample and optics, okay? Then you have your sensor, then your sensor will convert the photons into photoelectrons. You have some analog conditioning. So you have, maybe you shift voltages up, you sum charges, whatever. After that, it goes to an analog to digital converter. There you have some processing already very close, like this dual readout merging. You have correction of various pixels that could be hot, cold, etc. You might want to do some, all pixels do correlated double sampling. So you measure a pixel first, you subtract it from the, like when it's dark before you use exposure, etc., etc. You might also, most sensors have some dark, pixels on the side that are covered with gold so that they don't have any light through. So it means that you get your line, you can normalize that out. You have a lot of such processing in there. After that, the microscope guys also need to do some work on the image. They need to do stitching, they need to correct for various aspects that I'm not going to go into. And then also when you get the image, you're also going to get to do some stuff. Crop, maybe you need to register it. You need to do some affine transform, maybe if you're doing some particle detection on a subpixel level. You might want to stack, to bin, etc. So, but by the way, just a question for the audience. For you guys, what is a raw image in all these aspects? Like, do you have a, yeah?
In the lab, we call the raw image or the raw data what comes from the camera into the storage chip on the microscope.
Okay. Okay. Yeah. Yeah. So I think that makes sense. It's 16-bit frame before the stitching, and so I think that makes sense. And indeed, and some algorithms as well, like if you pay a lot for a good camera, usually, I must say that the algorithms that are inside, you can have some corrections that make, if you have an idea of how a camera should work, they can make the output data of that correction closer to your ideal of how a camera should work than the original data. So, but of course, if you have an algorithm where you don't know, like if you have an affine transform, for example, you might have some interpolation somewhere. So like you have some patches of your image will have half the resolution of other patches. It's, it's not, if you don't know how the algorithm will work, then it's more challenging. You don't want to, you want to keep the previous data so you can improve your algorithm later. And so that's why it matters, right? Because if you want to have, so first, if you want to keep the data, it's because you hope that you will maybe do something with that data later, right? Otherwise, you might as well just chuck it in the bin. And so what you hope is that you have some novel biological insights later from that data. And in order to get novel biological insights, you might want to do some novel processing, right? So you didn't, and then you don't know how data might react to novel processing unless, it's raw. Let's put it this way, right? And, or at least you won't be able to do it in an accurate and reproducible way. So if you have good raw data, then putting it backwards, it means that you will be able to answer those biological questions in an accurate way in the future. And so safe to process so that you can preserve it a long time and reuse it. Accurate, reproducible results. And also you need to have clear quality metrics. So maybe you also want to know what data is good and what data is not good enough for your for doing whatever, for you doing your scientific, to get your scientific result. Like, is the resolution good enough? So you need to know, well, can I tell from that picture that the resolution was the thing that I needed. And of course, I suppose you have a deconvolved image versus a non-deconvolved image. You can't judge a resolution with the same algorithm on both images, because you'll get a result which is not repeatable, right? Because a non-deconvolved image, if you want to deconvolve it later, right? So if you start with a deconvolved image and deconvolve that, I haven't done it, but I suppose it's not going to look great. So why do you want to process in novel ways? Because with ZI, we are trained with that. But now, if I ask you, look, on these two images, on the left image, which cells have cancer, for example? I'm not a histopathologist, so I don't know, but it's not something that stands out to us. Maybe if you're trained, it does stand out to you better. And some people have told me that they get a feeling for that, but it's not something that, that I can see. For the AI, you can train your machine learning so that they do stand out to the AI just as much as the strawberries stand out to us. Same thing here. So here is a picture of Rome. If you have to see all the cars, so we know what a car is, but if you have to find all the cars in that picture, it's going to be very difficult. For the AI, instantaneously, it can find all of the cars in just as easy a way as we see the strawberries. Again, the strawberries in the previous picture is only a few pixels inside. So here, the satellite, with a good AI, if cars are only a few pixels in size, you can see them. So now this is an assumption, but does this work for real? So is it real that if I now take a raw image that I can process in a way that is different than what I do with a human eye, I get a better result? So we put this to the test. So what we've done is that so this is open source, by the way. So on our website, you find out the GitHub link. What we've done is that we took a standard image processing pipeline, like the ones you would have in Photoshop, and we recoded that in PyTorch in a differentiable manner. So now you have an image processing pipeline. You can develop the strawberries, you can see them perfectly, or you can train it. So you can train the parameters of that pipeline to optimize for a specific task. And so in this application, we had first you needed some human labeling of different cells. Then you wanted to do some segmentation. Where is the cell? And then you wanted to classify what type of cell is it healthy or not? And what we've done is that we trained the image processing pipeline for each one of those sub-applications, so each one of those pieces of one single application. And we saw that indeed you can improve significantly the results if it's targeted to one specific application. So what we've done here, so here, when it says frozen, it means we just trained it for the human eye, and then we didn't move the parameters of the pipeline anymore. And as you see, it's saturated about 50% accuracy. On the other hand, if we let the neural network train the parameters together with the final task, it goes to like 75%. So this is a small part of the paper, just as an illustration, but you can look for more details. And if you want to use it, it's all on GitHub. So it's a bit of a complex thing. So maybe you have some questions at this point? No questions? Okay, so with raw data that looks not very good, you can generate these 3 images. So what's the downside of the raw data is that is rather big. And the cost of storing and processing data has gone down a lot in the past years. So for 10 gigabytes, it went from, in 1972, for about more than $1 million to about $3 nowadays. However, since 2011, it has kind of stabilized the price, the cost of storage, whereas since 2011, the cost of compute has gone down even faster than it used to go down before. So there's a bit of a discrepancy between the cost. So the relative cost of storage and compute has really changed, with the one of compute being much cheaper. And also the other interesting thing is that the the power of compute has gone beyond the one of human vision a few years ago. So now if you buy the latest GPU, it has more visual process, or roughly the same visual processing power as we do, for a bit more energy in. So what this means, and as well, the other aspect is that image sensors, there's more image sensors in operation today than human eyes. There's about 50 billion image sensors in operation nowadays. So it's only natural that that compute gets used to see effectively. That's how the machines see. So what you want is to, because it's so widespread, you also need to have accurate and reproducible results that are widespread. And if you've got good data, it means you don't need to take more data, right? So it's already a saving there. If you know this data is going to be accurate, you have a saving right there. You just don't save the rest. So there is, so this is some work we did before talking to people ourselves, and then we also merged this work with some work that was being done by Quadriplimi, that is a reproducibility standard for microscopy. And we thought, well, how have people solved this in different fields? So, like we don't want to reinvent the wheel. Let's see how reproducibility was solved in, electricity, right? Like you have your 230 volts plug. It's written on the plug. Well, that's the tolerance. It's written on the socket. That's the tolerance. That's okay. I can plug it in. And you have how many hertz it has, what the voltage, if it's AC, DC, etc. So we thought, well, there's a whole field, there's metrology. They wrote lots of books and about it. So let's take those concepts and let's see if we can, instead of having an image just as a picture, can we make an image into a proper measurement? What would the requirements be if we wanted the image to be a measurement, or a measurement result to be a bit more formal? So the first one is traceability. It means, well, if I have, how do I know that I had 2 photons here? Like, can I compare these 2 photons on my, that I got on my camera with the 2 photons on your camera? And what it means ideally is that if I buy a Leica or a Zeiss microscope, I get the same results. Whereas we also worked with World Health Organization, and we had some, to standardize the results of AI across instruments. And what we saw, like, okay, if you get more people with an illness in Berlin than Munich, it might be that just they have a different type of instrument. And that, in all likelihood, in your statistics, is that they have a different type of instrument, and not that they're actually worse, that they're less healthy. So in practical terms, if you have already quantum efficiency, pixel size, black level, and gain, that's kind of already, you're going really far. You can always do better, but that's really good enough. So if you, when you take images, write those things down. If you are like manufacturers now with this product Quadriplimi, they're going to put these values in the metadata every time. So you will get them in your pictures. And then the other aspect is you want pixels to be, so the pixel values that are measured to be independent. So if you take an average of 2 pixels, it's, if, for example, you a priori know that, I don't know, you already did some averaging and you binned everything together, or then you can't take an average of 2 values that are correlated, right? Like if you already took the average before and just stored the value the same, or did an interpolation or something, you can't do the same statistics in the same way. So you want to have your pixel values that are ground truth plus noise, but you don't want ground truth plus noise plus some part of another pixel as such. So if you take, for example, a deconvolved image, if you take 2 pixels on a deconvolved image, if you do the average of those, you can't say, oh, well, my uncertainty is going to go like divided by the square root of 2 or whatever it is, right? Because those are correlated, and you would need to have the correlation matrix, which you can't calculate for difficult algorithm. So you need to have this independence. Also for very simple stuff like mean and variance. The other aspect is that you need to have trueness or low bias or no bias. What this means is that if you have a systematic error that is always the same, for example, say you're taking a spectrum, and on your spectrum, every pixel has 0.1 photon offset, but then you integrate your spectrum vertically and you have 1,000 pixels, you're going to have, because it's always the same error, is going to add up. Same with pictures. If you have, for example, on the right, so this is our compressor on the left-hand side with with random error, let's put it this way. So it's not no error, it's got random error. So if you do any measurement, any statistics, that error will tend to cancel out. Whereas if you have another, so this is good old JPEG, because the errors are correlated, like I put the same picture on JPEG 10 times, it's going to 10 times give me the same artifacts. And those artifacts will add up. And then you can be in weird situations where if I expect that adding 100 images together gives me a better result, but you can be that adding 100 images together gives you a worse result, right? Because if you add every time more error. The other aspect that is really important, and you already have it in certain analysis algorithms like Storm, is to have to report uncertainties. So if you report uncertainties, so if a pixel here is very small with a small uncertainty, it means that I can count, it counts much more, right? So even if I have only one, because the uncertainty is 4 times smaller than that one over there, I can count this pixel 16 times more than that one over there, because this uncertainty is a bit smaller. And so if you report the uncertainties, and if each pixel, you know how much it is, then you just gain, is like if you had free data, right? Like lots of free data. Now let's give, okay, so if you do all this, you can call your data raw. So if you have reported uncertainties, you have low bias, you have independence, and you have in principle traceability. Then if you have that on one instrument to the other, comparable. Now let's give some practical examples of where you might get a defect. So often I heard someone talking about shading correction earlier. So typically say like you do your shading correction and it looks, like because your edges of your frame, they look a bit darker, right? So you multiply those up. But then what you do is you put that through a machine learning system, and the machine learning system anyway is gonna take out your DC level right away. You're gonna do minus divided by the variance minus the mean or whatever. So you're gonna take the AC component of your signal. So and when you take your AC component, you're back to finding the extra noise you had, because now you multiplied the edges, so like the noise you had in the edges got multiplied up. And because you removed the actual signal to be sensitive, now you see a lot of noise like here on the edges, and whereas it's going to be quite away from the ground truth. So correcting, like if you correct just one statistic, like the amplitude, and not correct all the higher order statistics, if your algorithm relies on some higher order statistic, it's not going to work. And that's what like machine learning does, right? Like you have lots of kernels and each kernel does a different higher order statistic. So you have to be careful about those things, but it doesn't mean that you can't do operations while preserving all of the previous properties, and why you can't do shading correction in such a way that it preserves all the statistics. It's completely possible. You just have to do it. And this is pretty much for most operations. You can find a way to do it right. And same for stitching. So University of Geneva, they saw, yes, like we stitch the images and we see different cell counts at the seams of the stitching. They said, yes, well, actually, because you have less noise, so like they had this threshold, and you had less pixels going beyond the threshold, and that was it. But so, for example, you can add a bit more noise if you do it just right. You need to trace how much noise you had from the camera. You add a bit more noise where you need to have it, and then you solve that problem. So the point is, if you manage to do that, there's no, you you could, if you do it right, you could call your output data of that still raw. Because the other aspect is that you can't be too absolutist on these things. Like the data is never going to be perfect, but it doesn't really, how much does it matter? Well, it matters if it gives you a different result, or it matters if you can't use the data for other type of processing in the future. The manufacturers, like if you tell them, well, it's give me just what comes out the pixel value, they're stuck, like they say, well, no data is going to be raw. So you need to find a good definition that is valid for everyone, that everyone can agree upon, and that everyone can work with. And that definition is, well, my pixel value is a measurement result with the right uncertainties, with everything you need. It will work well. The other aspect is clear quality metrics. So this looks like a complicated equation, but it means if you have a quality metric, what it says is, well, you want some value that becomes better as your result becomes better, right? So it's a monotonous function. So like if you want to detect fluorescent particles, you want that if you have a quality metric like signal to noise ratio, that the more signal to noise ratio you have, the more particles you detect. So that's simple enough. On the other hand, some metrics, and this is what, so here we get a bit more into compression and the ways why we did the compression differently, is that for the human eye, and this is JPEG, so this is JPEG, I took JPEG 2K here. So for the human eye, so the intent of JPEG was like, I process my image, and then I compress it, and I distribute it for humans to look at. And when you do that, well, you don't want to have defects where you can see them the most, right? So like if you have a very bright, very visible area, that's where you don't want to have a defect. And you optimize, and there's a metric which is called peak signal to noise ratio, which somewhat correlates with that. And you optimize to that, and you get, like, the more dBs you get, it means the better it is. And JPEG 2000 is really one of the best compressors with respect to that. But for machine vision, and especially if you want to do segmentation or to look at cells or something else, you want exactly the opposite. You want to say, well, actually, like, if I can see something perfectly, if I lost a little bit, I'd probably be fine, especially if that little bit is way smaller than the original noise that I had on that pixel value. Whereas if now I have something which is very difficult and very hard to see, that's exactly where I don't want to lose anything, because it's going to impair my machine vision then, right? I want my machine vision to work exactly the same. And so this means that your machine vision then will work still really well on the really high, on the really good, well-exposed data, and it'll still work really well on the really dark stuff. And so it's quite interesting, because also a simple test we did is we took the camera and we took an original, so the original one. We made the JPEG, and the signal to noise, the peak signal to noise ratio, so this specific metric, was 62 dB. And then we took a second original, and we measured the peak signal to noise ratio with respect to the second original, and it was 51 dB. So way worse. But of course, the second original is just as good as the first one, right? And it can't be worse than the compressed image. And interestingly, we put, so these compressors, so, they are roughly actually in order so this one, for the human eye, this one is okay. This one, they improve it further, and like we think we improve it further. So interestingly, anti-correlates with that metric. PSNR
is a pairwise measurement? So
yes, you need two images. Like you take one image minus. So strictly speaking, if you take the strict definition of PSNR, this is why the mistake comes, because the guys who came up with it were good, but it's with respect to ground truth. Because when they came up with it, you didn't have really a lot of digital imaging. So like your original image was the ground truth, right? So you compare both. But nowadays, you can't technically compare it across two real images. Like if one is not absolutely correct. So if you took 1,000,000 times average on the first one, then it'd be a good metric, kind of good. So if we take a different metric, and one should take ones that are useful for themselves. But here what we've done is we've taken a metric, for example, difference in standard deviations from the original value. Here I binned it in 8x8 tiles because otherwise the screen is not big enough, right? But you see that now the picture you get is very different. So for us, this is okay. So it's really good, but this is also what we optimized against. So not just like chance that I chose this one, but whereas the other ones are worse for this metric. Also, another interesting thing is if you take PSNR, like the other aspect is that for humans, like we see an entire picture as one, and the way that I believe all the other compressors were optimized were over the entire picture. So let's minimize this value, sum of square differences or whatever, like over the entire picture. And what this means is that if you have some localized loss, it's okay. Doesn't matter. You might save a lot of noise in the highlights and lose a lot in your shadows, and that's fine. You might still optimize your PSNR. And so here's an example. So I took JPEG XL. So JPEG XL, by the way, is a really good compressor. And I pushed it. I saw, well, how much can I compress with JPEG XL until I have the same PSNR as I have across the two originals? And I could compress up to 20:1. And as you can see, however, the results weren't very good. So here I had like more than 10 standard deviations away from the original. And then I had a different, another experiment, which was how many pixels can I delete from the image and still keep the same PSNR as with across two original. And here was about, I could delete 12% of the pixels. So 0.5 megapixel on, this is a Hamamatsu camera frame for megapixel. So really this PSNR value is not really useful. And interestingly, there are not a lot of good metrics that correlate with measurement results right now. And so this is also what we're working on Quadriplimi is like, well, let's try and find some. So if anyone is interested in that, I do working group 10 in Quadriplimi, so please join if you have any ideas. And so the ideas also mean like what you're interested in, like if you say like, for me, this is really important, come and tell us, because the existing ones are not very good. So managing raw data at scale. So you came by bike, and then we look at, well, but it's unfortunately, a lot of the stuff that we can do on our personal lives, they don't impact very much what we do. So I spoke to this Swiss CTO of Microsoft. They say a new rack in the data centers is up to 200 kilowatts, just one rack, and the limit of the size of the data center is how many trucks diesel trucks you can fit on the road to fill in the diesel generators in case the nuclear power or whatever it is goes down. That's the limit of the size of the data center. So what you see here, all these boxes on the side, those are diesel generators. This is a Microsoft data center. Size approximately like EPFL. And it's very difficult for us to like imagine if we see like, 1 terabyte, you can have a micro SD card, that's 1 terabyte. But if you imagine like 1 petabyte, it's probably going to be one big rack. But then like if you have like an exabyte, so maybe this has maybe 1 or 2 exabytes, like scale, right? So for us, like mentally, it's difficult to do that multiplication, but it's micro SD to this. And everyone is looking at, oh, well, how can we generate more power? Do we have like fusion, etc.? But what we look at is say, well, actually, like now I think the lead time on any power station, like gas, a turbine, like it's at least 8 years. So if we want to go, and for example, like in Switzerland, 2023, there was 4% of the electricity was used for data centers already. And that's as much as the trains, put into perspective. In Ireland, I think 2023, they had also 4%, and 2024, they had 40%. So, I mean, it goes quite quickly, right? Like one rack is 200 kilowatts, and you know how many racks we can fit in EPFL campus size facility. So we just don't have that much electricity. So like we believe, well, we have to like find other ways to reduce the power consumption and other ways to optimize how your processing and storage of the data works. So this is our goal as a company. And we hope that we are more effective than other things that we can do in our personal life. So like my colleague looked it up and said, well, you can either reduce your heating for 37 years, you can eat locally for 15 years, you can become vegetarian, or you can compress 100 terabytes of microscopy data with JETRO to offset a flight to Japan. So thanks a lot. So you can go to Japan with a clear conscience. So yes, it can have a really big impact actually. And if you keep the data for 10 years, then, you know, like it's even better. So what we've done, some of you use this and some of you participated in developing this. So thanks a lot, first of all, for all your help. I know that it has needed lots of patience and maybe a little bit more will be needed. What we have on JETRO is we wanted to make those savings easy to use. What we had before as a compressor, it was a bit, so we had the Fiji plugin. I mean, we still have a Fiji plugin, you can still download it. But what we saw, it was very difficult for people to manage that. Maybe they had a different software. Maybe they had an install of Fiji with a very specific version. And like matching everything together was a bit difficult. And especially like Windows, Linux, Mac, we had 45 different Fiji plugin versions that we maintained. So yeah, it wasn't scalable. So what we've done is that we made it more transparent, because also everyone likes their own file format. Some people say, I want just the CZI. Some people say, I want only TIFF. Some people want ZAR. Some people, so everyone likes their own format, right? So what we said is, well, like, can we hide the complexity of the compression in the on the background, so that you don't have to worry about file formats anymore. You don't have to worry about plugins anymore. And so what you have is, by the way, like you guys have a license. If you want to try, you can download it from our website and try it out or use it. And is that you have a file, it compresses in the client automatically, and then it puts it on the server. And then when you load it back, it just decompresses again. So you work with your own files. So you can do this on your desktop. On Windows, you can mount it as a drive. And also you have a Python API that you can use if you process your files. So, and you shouldn't worry about if it's compressed or not. So this is a little video that Ariane did. So especially if you work with the cloud. So the second fastest transfer system is called S5CMD. It's from Amazon, or maybe not from Amazon, but it's on Amazon S3. And what you see is that we finished in 12 seconds, and this still needs about 2 minutes more to finish transferring that. So like, I think we save the money, but actually you also save time very, very much. And this is what 7 times as well. You don't feel it. We don't feel scales. We set at 7x, but it means 1 day or 1 week in practice. How our compression works is that you have your image, and we also have physical models. So like kindly the microscope manufacturers, the camera manufacturers, they all spoke to us. They said, this is what we do with the image first, so you understand how it works. These are the parameters. This is the noise of the camera. This is how you can predict it. And now, effectively what we do, and this is a bit unintuitive, but we add a little bit of noise to the image according to the correct camera model. So it's like your output image is as if your camera had been a little bit more noisy, but it's still on a pixel by pixel basis, and it complies with all of the all of what people think that means raw. So the output image is still a raw image, but now that image, and it's also like big like a raw image. It's, you know, it can be in any format, it can be in any file type, but is now, because we understand the noise so much better, we can compress it by 7x. And also the other aspect, so compression, so you can get 7x better, but it's not the only way you can save size. Like another way is you can generate synthetic data and maybe save even more. And the more you know about the camera and the noise, etc., the more accurate synthetic data you can generate later. So this is, if anyone is interested, so these are more advanced tools, like but they're available to everyone in the API. You can use those. What you can do is, like from one image, you can maybe generate 2 or 3, depending. You still have a photon budget, so you know information doesn't come for free. But depending on what you want to do, you can get some extra power out of your image. Don't know if this is, so I went very light on the technical side. If someone wants more of an intuition of how the compression actually works, or technical explanation, yeah, more of an intuition. Okay, so this is because it's not, but I found one the other day that maybe it makes it intuitive. So basically, compression, the way it works is that you try to predict. So you load your image from left to right, and you try to predict your pixel value as well as you can. And now, if I predict, so say typically I have a 16-bit image. If I can predict to within, say, 500 the accuracy, it means that I only have to store the difference between the 16-bit value and whatever I predicted, and that difference is 500. So instead of 16 bits, I only need 8 bits. However, usually that 500 is very noisy. And now imagine that that instead of having the pixels one after the other, what you want to do is you want to, that time series is a stock market. And you want to predict what the value of the dollar, whatever it is tomorrow. Okay, well, that's maybe too easy to predict, but like the value of, I don't know, euro tomorrow is. And now it's going to be really difficult and really noisy. So you're not going to manage, and you still have to use this 9 bits to store the value. On the other hand, now suppose you're a really rich guy, and you can start putting a little bit of money in the market to buy or sell euros. You're going to start manipulating the market a little bit, right? And if you do it in a random way, no one's going to know, because you don't buy or sell in a systematic way, but you do it in a random way. You don't even decide yourself. You just have a random number generator that tells you, buy so many euros. And it's going to influence the market a little bit, right? So it means because you now influence the market a little bit, but no one else is going to be able to see it, because, like if you don't look at your random number generator, also you won't know. And you're going to influence a little bit. And if you know exactly what the variability of that market is, well, then you can make sure that it's imperceptible, or barely perceptible. You have a tiny extra bit. But now if I do have the random number, I know how I influence the market, and I can predict a lot better. So instead of predicting to within 500, I can predict within 10 maybe. Right? So if I invest a lot of money, I'm going to determine the price completely. If I invest just a little bit, because I'm going to say, oh yeah, I'm going to pay 10 francs for the euro, then the euro is going to be 10 francs, exactly, right? And so, but if I influence it just a little bit, I'm not. So if I only buy a little bit, it's not going to influence the book. But there's a right middle ground where it's imperceptible, but I still influence a little bit. And that's how Jetro works. So we add a little bit of extra noise, and so that we can predict better what the next value is. And that noise is modeled on the camera in such a way that is imperceptible, or that is just the extra noise, but the output of your the output image is still a raw image with the profile of the camera that you took. Yeah.
Yeah, so you were talking also about wavelets and things like that for your compression, because so I didn't get it exactly how much you compress.
Yeah.
So I get this idea that at the end you kind of, add a little noise to make it, kind of realistic, or
in the beginning we had the noise.
Yeah.
It's added in the beginning.
Yeah. But do you use wavelets or things like that?
No,
not
no,
at all.
not at all, not at all.
No. So what do you use?
So here is not in the transform domain. Here we do it in the real domain. It's in the normal domain. So in the actual pixel value.
And so when you say 7, so you compress by factor 7.
Yeah, 7 to yeah. So just predict like so the idea is indeed you'd add this little bit of extra noise to make the value more predictable, and then you just use a very good lossless predictor.
Okay.
So yeah.
But so that's strange that you don't use any transform domain. Why that?
So we because so this is something that we still have to study. The problem why we don't use it is that if you have, at least we don't know yet, how to correlate your like you get well, first we don't want to introduce false correlations across pixels. And because if you have some nonlinearities, and with especially in some higher order parameters, so like in your standard deviation, like it goes like the square root. So it means that if you now use a transform domain, so a transform in the linear domain, but now the noise is in the square root of your signal, roughly, then it's hard for us to predict how the wavelets the linear transform will affect the higher order terms. It might do it in a nonlinear way. So you might introduce some correlations if we're not there originally, let's put it this way. Across, like for example, like if you take JPEG 2000, what you see is like you see that you have certain path, like if you can get certain patterns.
Yeah, because I mean the artifacts, they will always more or less be the same.
Yeah. So we believe that there is a way to do it. We just don't know yet how.
Because you could.
But no, yes.
Yeah,
so this is
randomized wavelets or things that
we try to.
I think that what's important for you is that at the end, let's say you can do this averaging. Okay, so that's I guess an important. So that and that you can do training also. Huh?
Yes. Yeah. Exactly. Yes. Exactly. So we would like to. So we are working on that. We would like if you know anyone who would like to collaborate with us to push the next version, we're super happy. But for now, we haven't managed yet. But there is a possibility that it could work. Any other questions? Right. So we started with as a compressor. Now we went. So Ariane, for the ones who you know, like she has this very ambitious project, is where we've been investing a lot of our time and effort, is to help more with the data management. Like what we started is we saw what so we have some really large clients, and what they do is they need to move petabytes, lots of petabytes from A to B, and we started to see what problems they have. And it's just not easy, because also the time it takes to move a petabyte, it can be really a long time. And so we also built the infrastructure, and are still building the infrastructure of how you transfer in a good way lots of data from A to B. So here we are always interested in knowing what your specific problems are. So it's actually way more complex than what we thought in the beginning. There's lots of security stuff. There's like when you have long transfers, everything can happen in the network. You have firewalls, you have like so we've been going a bit crazy in the past. So we launched in February, but we've been going like quite crazy trying to find all the things that can go wrong. On the other hand, for quite a few things, it goes very right. So I do some demos. Like the other day, I was in Prague at the biology facility, and I had only Edge, you know, on the mobile phone, and I could do a nice data transfer on Edge, connecting with the computer. So like also like between Zug and Lausanne, I often do data transfers. It works great from the train. So some stuff also works very well. And an aspect that we try to keep is the workflow, so not to impinge too much on the workflow. So as well, like you have the full GUI or command line. On the other hand, if you're interested, also the back end of that is open, so you can use those directly, the APIs, if you want to integrate it in your own workflows. But especially we work with the manufacturers to integrate CZI, ND2, also VSI. We want to integrate OMISA soon, TIFF, of course, and also to work with different storage types. We like S3 or other S3-like systems, local or cloud, NAS, etc. So also you have a command line, a desktop Python. So it's quite a lot. It's a bit multiplicative, I must say, but it's a big project. But that's why it's so important to have your feedback, because that's when we know, okay, we need to focus on this part of it, because that's a really important part. So yeah, very open to the feedback. So we are in Zug. So we a spin-off of University of Geneva originally. However, it was founded by my wife and I, and in Geneva they had very big shortage of kindergartens, and a lot of startups in Switzerland, they moved to Zug. They say for tax reasons, unfortunately, as a startup, you don't end up making a lot of money, so I think you wouldn't pay taxes anyway. But it's a lovely place. So that's the actual real view you get from pretty much everywhere. And yes, so we also work in standardization, so different activities. So this AI for health, also Quadip, we try to participate, and also we work with Google and Meta. We were one of the three also initially to like do open data exchange standard. Like if you're a machine, you don't have Google, right? Like if you want to look at across of data, well, you have this thing, it's Croissant. So my colleague Lewis, he worked on that a lot, and it became quite popular. Not sure really how mature it is either, but it's used a lot. So yes, thanks a lot for your yes. So this I wanted to cite a lot the work. A lot of the things I presented here were the result of talking to people, quite a few people, especially in the context of Quadip Limi, and we would like to talk to even more people. So if you so feel free to contact us and to join the initiative. Thanks a lot.